Hello everyone, my name is Snigdha Bhagat and my topic for the project is facial expression recognition using deep learning. Introduction. Expression is one of the most powerful natural and universal signals for humans to convey their emotional state. The applications where facial expression recognition is used are HCI systems, which is human and computer interaction, surveillance systems, robot assistants, and driver monitoring in self-driving cars. As you can see, facial expression recognition has a wide variety of use in real life and the real problem that needs to be solved. Problem. FER, which is facial expression recognition, is an age-old problem which has been repeatedly solved with almost 90% accuracy. But this accuracy is not true as these experiments were done under controlled conditions where models faked the emotions and the methods could easily accurately predict that. Now, where does the problem exist? The problem exists when these methods were applied in the real world data. So when they were applied in the real world, that accuracy fell to 50%, which is bad. So how do we solve this problem? For every problem, the solution is deep learning. Similarly, the solution for this problem is also deep learning, especially CNNs. Motivation to take on the problem. So as we know, there's an increased amount of human interaction in today's modern world where applications are arranged from image filters to robot assistants. So the increase in AI applications and image-based contents, there is a surplus need for better expression recognition. Also, there is an increase in use of AI in healthcare where patients monitoring mechanism and systems use FER on daily basis, and once again it has gained a top spot for the future research. The paper which I referred to is Facial Expression Recognition with Deep Learning, Improving on the State of the Art and Applying to the Real World. It was submitted by the research team at Stanford in 2020. FER 2013 dataset is the benchmark dataset for the facial expression recognition with over 35,000 images divided into 7 categories of 7 emotions, which are sad, neutral, disgust, happy, angry, surprise, and fear. Works in facial expression recognition are: first, attention networks. The network dynamically adjusts the feature map of convolution layer for each data sample so that it improves the fitting ability, which overall increases the accuracy by learning better features. Second, data augmentation. So there is a novel approach to data augmentation using style transfer. Style transfer is a technique where a style from a source image is transferred to a target image, and this style changes the features of the target image so that the distribution of the image changes. Third is network ensemble. This means that multiple networks are combined together to create a new network, which in turn outperforms the individual network. The research has shown that these assemblies are really useful and are a future of FER research. What I have done, basically, I extracted the FER 2013 dataset from CSV file to PNG images. As you all know, images are just matrix of numbers, so in this case, that matrix was flattened out into a comma separated file of pixel numbers. After extracting those pixels to PNG images, I pre-processed those images to grayscale and resized them to fit the model structure. Now here I also used some data augmentation techniques, but they were directly implemented using Keras image generator, where it on the go converted the data with augmentations like horizontal flip, vertical flip, cropping, and resizing. After that, I used those pre-trained models which were pre-trained on VGG face dataset, and these models were used for transfer learning. I'll explain transfer learning in the coming slides. After this, I trained the pre-trained models on the FER 2013 dataset, which I also told that is the benchmark dataset for FER. And after training the model, compared those models for accuracy. One more thing I did was that FER 2013 has some class imbalance where some of the classes have fewer images as compared to other classes. So I used the Keras class weight function, which calculated the class weight for each class, and I used that in training as well. CNN. CNN stands for Convolutional Neural Network. A CNN is a type of neural network designed to understand various temporal and spatial features of an image. The CNN architecture is based on the structure of human visual cortex in the brain. What happens in CNN is that it is multi-layered neural network where each layer uses filter to extract different features. Above is an image where you can see that the green filter one is applied on the small parts of the image matrix and a feature is extracted from that matrix to create feature map. Each CNN layer has a convolutional net which can extract low level and high level features separately using different filters. Each feature is passed on as an activation function to the next layer, which extracts another set of features. As you go deeper in the network, the deeper layer extracts more complex features such as corner textures, etc., while the starting layers extract low feature like horizontal and diagonal edges. One of the reasons CNNs are so popular is that they are computationally less expensive than the fully connected counterparts. See, this is the architecture of CNN. Here, there are multiple layers like max pooling layer, convolutional layer, and fully connected layer. So as you see, the first convolution layer has a filter size of 5 cross 5 and it takes the input image and creates a feature map which is passed to the max pooling layer which decreases the size of the feature map and reserves the most of the information. Then the feature map is passed to the convolution layer 2 which again extracts complex features and pass it to the max pooling, which then transfers it to the classification network where it classifies into different classes. These are some top CNNs for visual image recognition. So, what is transfer learning? Transfer learning is the reuse of a pre-trained model on a new problem. The pre-trained model uses the knowledge that it has previously learned from the previous training to increase prediction accuracy on the newer task. Why do we need transfer learning and what is the reason? First, we do not always have big enough data set to train a deep network. Secondly, to increase the resiliency to real world data by training on different distributions of images. Third, there is always not availability of good hardware. These deep models sometimes take weeks to train on the big data set it to properly learn to extract features from an image. Traditional machine learning, both the models are trained on two different data sets and are then used for predictions. The case of transfer learning, the machine learning model 1 is trained on the data set 1, then its knowledge is used on model 2, which is of similar architecture. Now this model is with previous knowledge is trained on data set 2, so the combined knowledge will have better prediction. This is a screenshot of VGG model which I trained. So it has a prediction accuracy of 70% and this is the VGG model with class weights. So its accuracy is not changed much. Here is the ResNet model without class weights. As you can see, ResNet 50 model has outperformed VGG model with 71% accuracy, which is quite good. Um, Class weights, the accuracy of ResNet has increased from 71 to 73%. So the model has an average prediction of 71%, which is lower than 75%. As I told you earlier, this is because of the author trained this model on extra data sets that I didn't have the access to, so my accuracy is a little less. Also, there is a result of how the models perform. As you can see, where an image from different classes and below is the occlusion map which shows which part of the image is decider, and the red area shows the part with the most impact on that decision. Future work, I want to find better pre-trained models, and by reading current research, I want to increase the efficiency of ResNet and VGG models. At last, I want to use newer datasets. Thank you.